Now, this is a particularly difficult NMR problem that some students find difficulty with every year. I'll take you through it step by step so we can actually see how we solve this particular problem. I'm going to show you a previous example that we've done where I showed you about double bonds before I jump into this. In this particular example here, you'll see that we had a system like this. Remember, we assigned A, B, C, and D to these particular resonances. I'll just quickly run through this. Is that we had 3 protons on the double bond and all between 5 and 6, and then we had another doublet here which was the CH2 group, de-shielded because it had a bromine atom on that appearing around 5. So we had 4 resonances, 3 of them for protons on the aromatic ring, and then the extra one for a proton on a carbon attached, for protons on the double bond, and the extra CH2 for protons on a carbon attached to the double bond. So go back and look at this video and see what we did here, and keep this in mind. Now we're trying to solve something where we have a similar spectrum, because we have a double doublet here, a doublet here, and a doublet here, and we have 2 other groups, or 2 other fragments that I can actually make another fragment from these 2 particular groupings or resonances. So the fact that I have a resonance around 6.4, 6.5 indicates that I do have a double bond in my structure, and that there is a proton on that double bond. If I look at the spectrum, this region here where I find this doublet and this other doublet here, although you can probably see from now that that coupling constant is slightly larger than that, and remember I told you about 8 Hertz and 16 Hertz, so this proton is probably a trans proton, that's probably a cis proton, but this doesn't really lie between 5 and 6.5 where I normally get my double bonds. So this is a bit more shielded than usual, but let's leave that aside for now. Let's just go to these other 2 resonances here. I have a typical triplet and a quartet. A triplet at 1.2 or so, a quartet at 3.8, which means that there must be something de-shielding this CH2. I know it's a CH2 because it integrates to 2 protons. This integrates to 3 protons. It's probably a CH3, and it's a typical quartet and triplet for a CH2 CH3 pattern that we've seen so many times before. And the fact that this is de-shielded, it must mean that it's next to an electronegative atom. The only electronegative atom I have in the molecular formula is oxygen. So I have this particular grouping, or this particular fragment, and then this particular fragment. If I look at my carbons, 1, 2, 3, 4 carbons are fine. I'm taking care of the oxygen. 8 hydrogens, I've got 5 here, 6. So I need to put another 2 hydrogens on there and put the other group in the remaining position. It doesn't really matter where I do that, because they're going to fit around the aromatic ring in that fashion. So I have all my groups here. Let me try and make sense of this. So this is the solution to this, and I just place my atoms, remaining atoms, on my 3 positions of my double bond, and everything fell into place. But let me look at this structure and try and analyze this structure a bit more carefully and see what's going on here. And I look firstly at these protons here, that proton there, and that proton there. it's distinctly different from this hydrogen on this carbon, because in this carbon I have oxygen directly bonded to it. So it's oxygen, carbon, hydrogen, and that's why this proton is here, so de-shielded, because of this oxygen atom. So this hydrogen is responsible for this double doublet here, and I'll come back to this double doublet just now. But I'll bring your attention firstly to the two other protons. This proton is orthocoupled to this hydrogen here, so it must have a smaller coupling constant than this proton, which is transcoupled to this proton across it. So this proton has a trans coupling, this proton has a cis coupling. Your trans coupling, I said, is normally 16 Hertz for trans coupling, and your cis coupling is normally around 8 Hertz. So if I had to label these as A, B, and C, your A proton would be this one with a larger coupling constant, the B would be this one with a smaller coupling constant. There's your CH2, there's your CH3, and the C here with the double doublet would have a coupling of both. If I look at this particular peak, these two, the first line and the third line, you'll see that, and I'm showing a big expansion here, so that first line and the third line is your 16 Hertz that you see, and the other two, there and there, the first line and the second line, is the 8 Hertz. So how that arises, and let me show you on the side here, is that A will be split by C with a coupling constant of about 16 Hertz, and I'm just exaggerating the length here. So if that is 16 Hertz, and then so A splits the C into 16 Hertz, and then B splits the C into 8 Hertz. So each of these are split further into 8 Hertz to give you the 4 lines. Alright, so I did a very bad drawing here, but normally this would be 4 equal lines here, because I can see a 16 Hertz and an 8 Hertz, so it will look something like this. Right, so the point I was trying to make here is that the first doublet is split into a further doublet, giving us 4 lines that we see here with the coupling constants of each of these, A and B. So this is a nice example. The effect of having an ethoxy group on this double bond somehow shields the resonances of A and B, so they're no longer around here, they fall in that region. So this is a nice example to note of an NMR spectrum where we have protons on a double bond.